Hello, are you getting?
Hello? Yes, sir, I can hear you.
Okay, okay, just a minute. Hello.
So, can you hear me?
Yes, I hear me.
Yes, sir, I can hear you, sir.
Okay, so okay, now I think it's okay. So first question, very simple
Yes, sir.
question. This
Yes,
first
sir.
question. In this question, just take out your paper. Okay, on.
Yes, sir, yes.
Just- So first question is they are saying choose the quantity with SI
That's right.
unit ampere per meter square. Very easy question.
Yeah, ampere means current, meter square is
Yeah,
length. Square.
ampere meter square. So first option is given. First option is given. Magnetic dipole moment.
Yes.
First option A is given for question number 1. Option A. Magnetic moment is given by current into area.
Yes,
If
sir.
n is equal to 1. So current into, so just what is the unit of current? Ampere. And what
Ampere,
is, and unit of area is meter square.
meter square.
So first option is ampere meter square. So this option is not correct.
Yes,
So
sir.
now we will check for option number B, conductivity. So
No, sir,
conductivity is
conductivity.
sigma. Conductivity is 1 upon resistivity.
1 by resistivity, yeah.
Yeah. So we can calculate the unit of resistivity, rho L by A.
Rho L by A.
From here, I can calculate R A
R
by
A
A by L. So
L, yeah.
from this formula, we can calculate the unit of resistivity. So unit of resistance is ohm,
Yes,
and
sir.
unit of area is meter square,
Yes,
and
sir.
unit of length is meter. So this and this will be cancelled out.
Cancelled. It will be
So
ohm meter.
yeah, ohm meter. So this is 1 by rho. So unit of this sigma will be ohm meter inverse.
Yes, sir.
So this option is also not correct. Option
Yeah.
number third, current density is given. So current density is J, and that is current divided by area.
Area.
So unit of current is ampere, unit of area is meter square.
Meter square.
So this is
Yeah,
your
so it will
answer.
be ampere meter square.
Ampere to the power -2. They are asking na -2. So this
Yes.
option is correct. Now for the
Yes, sir.
just I am this is finished, but I am just checking the option number D.
D.
So
Yeah,
D is the
resistivity.
resistivity.
Rho L by A.
So this is the unit of resistivity, ohm meter.
Ohm meters. That's
So this option is also incorrect. Okay, so your option number C is correct. Okay.
yes,
Second
sir.
question. Second question. I think I have already discussed.
Yeah, yeah.
So I am just discussing the question number third. So just I am just discussing the question number second also. Okay. Question number
Yeah.
second. They are saying two particles of same charge are projected to. Just take out your paper because you will not get which question I am solving.
Sir, I have it, sir. Paper.
Okay, okay, good. Okay, good. So two particles of same charge are projected to a region of a perpendicular magnetic field. Perpendicular magnetic field. Charge particle moving in perpendicular will follow the circular path. Okay, this
Yes,
is
sir.
already know. If radius of the circular path followed by the particle r1 is greater than r2, two particles are given. Radius of particle 1 is greater than radius of particle number 2. So formula of the radius of the circular path is given by mass into velocity of the charged particle, charge
Yes,
on the
sir.
charged particle, and the
Yes,
magnetic
sir.
field. Okay, so this will be m1 v1, charge is same, magnetic field is same. Okay,
Yes, sir.
m2 v2, charge is same, magnetic field is same, so this will be cancel out. M1 V1 will be greater than M2 V2. Check the option number C. Option number C, na?
Yes, sir.
Yeah, option number C. Question number
Um,
third. Question number third.
Terminal voltage across secondary cell is equal
Yeah.
to similar.
So secondary cell means the chargeable cell. The cells
Yes, sir.
which are charged, like the battery of this phone.
Yeah,
Okay,
like rechargeable. Yes, sir.
rechargeable. Okay, which is rechargeable. So here in this question it is given that they are saying the terminal voltage across this secondary cell is equal to its EMF, is equal to its EMF. So see here, you have this one cell here, and this is the, suppose here you have connected an external resistance R. This is the positive terminal, this is the negative terminal. Small r is the internal resistance, E is the EMF. So if the cell is charging, suppose the cell is charging, what is the equation of the terminal voltage for the charging? V is equal to E plus IR. Okay,
Yes,
this
sir.
equation you should know. They are saying uh, terminal voltage means terminal voltage is equal to EMF. So here I can put, instead of this V, E. This is also E. This will become IR. Okay, this IR is equal to E minus E,
Yes, sir.
and this is equal to 0. So this your current equal to 0 in this case. If the cell is charging, so your current is 0. Now if the, suppose if the cell is
Yes, sir.
discharging, so for discharging, the equation of terminal voltage V is equal to E minus IR. So put this E, this is also E minus here, from here also you will get current equal to 0. So first option is it is charging. So we cannot say it is charging. It is discharging. We cannot say. But
No, sir.
we
Yeah.
can say that current is
No.
0. Current is 0. So option B is correct.
Yeah.
Option B is
Yeah.
correct. Simple.
Yeah. When no current is transferred, sir.
Yeah. And question number this magnetic field, a circular coil. This is question number 4, na?
Four. Yes, sir. Four.
So they are saying
A
a
circular coil of
circular coil of 100 tons and radius 10 centimeter carry a current of 20
10
ampere. What is,
centimeter.
yeah, carry the current of this, and we will
20
find the
ampere.
magnetic
What is the
field
magnitude of?
center.
Yeah, it is mu 0 I by 2 r.
Yeah, mu 0.
I
Here
by 2
number of
r.
turns is given. So suppose in this coil 20 ampere current is flowing like this. Number of turns of this coil is 100 or 100. Current is, we know, 20 ampere. Radius is 10 centimeter. So when you will convert this into meter, you will get 0.1 meter. So the magnetic field at the center of the circular wire is mu naught Ni divided by 2r. Okay. So mu naught is 4 pi into 10 to the power minus 7. N is 100. Current is 20 ampere divided by 2 into 0.1. When you will calculate this, you will get answer 4 pi into 10 to the power minus 3 Tesla. Simple. Okay, got it? Your net gone. Harsh, now it's okay.
Yes, sir.
So see this question I have solved by using this formula.
Yeah.
All the variables are given here, all the values are given here.
Yes,
Okay, with
sir.
respect to this formula, you will get this. And now question number here.
5. Derive an expression.
Just tell me the question. What is the question?
So
Drive an
derive an expression for resistivity of a conductor in terms of relaxation time.
resistivity in terms of relaxation time. Okay.
Relaxation time.
So what you should do now for this question? What you should do? See here. Uh, question number
5, sir.
5. So take one cylindrical wire.
Yes, sir.
We have already discussed this. Okay, we have already discussed it.
Yeah,
Take
yeah, yeah. Yes, sir.
and connect this with a battery. Suppose the potential difference across this is V. Terminal potential difference across the battery is V, and suppose L is the length of the conductor, and A is the area of the cylindrical conductor, and N is the number of electron per unit volume,
Yes, sir.
and V suffix D is the drift velocity,
Yes, sir.
okay, of the electron motion. So we know that the expression for the drift velocity is given by E tau phi m. What is E? Charge on electron. E is the electric field.
Yes, sir.
Tau is the relaxation time. Tau is the relaxation time.
Relaxation time.
Okay. Tau is the relaxation time. One more relation we know. The relation between the drift velocity and the current. I is equal to A N E V suffix D.
A and EBD. Yeah.
Yeah. A N E V D. Now we will put this V D here. I is equal to A N E. Put V D here. This will become E tau by M. E capital E tau divided by M. Now there is a relation between the electric field. There is a relation between the electric field and the voltage. Electric field is equal to voltage divided by length. From this relation you will get E is equal to minus dV by dr. You will get. Okay. Now put the value of electric field, that is V by L. V is the potential difference. Okay.
Yes, sir.
V is the potential difference. So we will put the value. This will become A N E square. A N E square and tau divided by M, and this will become electric field will become V divided by L. V divided by L. Okay. Now take this V this side. So this will become I by V is equal to A N E square tau by M into L. Now reverse this equation. It will become V divided by I. So it will become ML divided by A N E square tau. What is voltage divided by current is equal to resistance?
Resistance, yes, sir.
Yeah. V is from the Ohm's law. V is equal to IR.
Yes, sir.
Is equal to, this is the resistance ML. So this is the microscopic form of resistance. I have already told you. But now here what you have to do now, you already know what is the resistivity. Resistivity is resistance can be written in terms of resistivity also. So R
Yes,
is
sir.
equal to rho L divided by A. So suppose this is equation number 1. This is equation number 2. Now compare the equation 1 and 2. You will get the value of resistivity. Compare equation 1 and equation 2. See, here is L by A, here is L by A. This will be cancelled out. So resistivity will be M upon Ne square tau, Ne square tau. So this is your resistivity in terms of the relaxation time.
Yes, sir.
Resistivity. So what you have done, you have compared the equation number 1 and equation number 2. You will get the resistivity value m upon n e square tau. Next question.
Next question, sir. That's then there is an or question in that also.
Or
A
means you
cell
can
of EMF E and internal resistance R is connected across a variable resistor R. Plot a graph of showing variation of terminal voltage V of cell versus the current I using the plot show how EMF of a cell and its internal resistance can be determined.
okay. So this type of question I have discussed in the assignment. Now I am just again discussing. So this is our question. Okay. So see, here a cell is given. R is the internal resistance.
Yes,
Okay.
sir.
R is the internal resistance, and this is connected across a variable resistance R.
R.
R is variable here. So this is positive sign, this is negative. This is positive terminal, this is negative terminal. So the terminal voltage of the cell will given by E minus I into small r.
Yes, sir.
E minus IR. So this is the equation of the straight line. This is the equation of the straight line. Just how V is equal to minus R into I plus E. So this is Y is equal to mx plus c. M is the slope, c is intercept on y-axis. So you can draw the graph between the voltage and the current. This is the voltage, this is the current, and
Yes,
you will
sir.
get a graph having negative slope. A graph having negative slope you will get. Okay. A graph having negative slope.
Negative slope.
Yeah. So slope will be this. Compare this. This slope will be minus r.
Yes, sir.
Slope will be minus r.
R.
So internal resistance of the graph, internal resistance, okay, internal resistance of the cell is given by negative of the slope.
Yes, sir.
Okay, negative of the slope. You will get the internal resistance R. So they are asking how you will find the internal resistance and the terminal and the EMF, how you will find. So EMF we can find easily from this equation. From this equation, put the value of current equal to 0.
Yes,
In
sir.
this equation, V is equal to E minus IR. When you will put I is equal to 0, you will get V is equal to E. So here at this point, when your R is equal to 0, so this value will be your E value. This value will be will be 0 comma E. Okay.
Yes, sir.
So you have just this length, this suppose this O, this is P, and this is Q. So OP value is equal to the EMF of cell.
Yes, sir. Sir, just a minute, I'll write this down.
You are writing?
Yeah, I'll write this one because I didn't attempt this question. I did the or part.
Okay. Next question I have told you in the class also.
Yes, sir. Galvanometer, high resistance.
Galvanometer we will discuss today, I think. And the next question I am talking about next. Using Ampere circuit law, drive the magnetic field near a current carrying straight conductor. Draw the graph showing the variation of magnetic field with the distance from the conductor. This question I have asked. I have told you. And again, next question is the how do
force
you
between two parallel plates conductor.
Yeah, how do you convert a galvanometer into voltmeter? So galvanometer into
high
voltmeter
resistance in parallel.
no, higher resistance in series.
Ah,
Yeah.
no. So galvanometer to voltmeter, right? So voltmeter is the highest resistance. You will put high resistance back.
No, when you will put the resistance in parallel, your net resistance will decrease. But when you will
in
place
series, sorry, yes, in series.
series.
Parallel is for ammeter to galvanometer.
Yeah. Parallel is for ammeter only.
So can I scroll up? Oh, just a minute, I'll write this.
You have completed this now?
Yes, sir. Can I scroll up?
Scroll up.
Yeah. That question only. Which one? EMF of cell. Yeah, this one. This one.
Your paper is was very easy.
Yeah, it was.
Just you can write.
So can I scroll down? So
yeah, scroll down.
Yes, sir, down to the graph. Yeah.
Okay.
Yes, sir. You can continue, sir.
Okay. So next question is the plot the variation of resistivity of semiconductor with temperature. I have explained you na this question.
Yes, sir. Semiconductor.
In the class. Again, I am explaining again this question. Question number? What is the question number?
Seventh.
Okay, seventh. Question number 7. So in question number 7, they are saying the plot the graph of resistivity with temperature. So how the resistivity will vary with temperature for the semiconductor. Semiconductor, very simple. You should know the formula of the resistivity. Okay. Resistivity formula is given by m upon Ne square tau. Okay. Talking about the conductor, the mass of the electron will remain same. Okay.
Yes, sir.
And charge on the electron will remain same. So you can say your resistivity will depend upon the number of electron per unit volume, and your resistivity will also depend upon the relaxation time.
Yes, sir.
Relaxation time. But in case of semiconductor, this n value is very small. N value is very small. So when you will increase the temperature, you will increase the temperature and the bonds inside the semiconductor will be broken. So this number of electron per unit volume will increase. So resistivity of the semiconductor will decrease.
Yes, sir.
But for the relaxation time, when you will increase the temperature, so as we know that there are a small number of electrons, free electrons inside the semiconductor. So relaxation time will decrease.
Yes, sir.
Will decrease, but not significantly decrease due to the less number of electron in the semiconductor. Okay, so this factor will be significant. So here relaxation time will decrease, means resistivity should increase, but this factor is insignificant.
Yes, sir. So just a minute.
Okay,
Right,
just less number of charge carriers. So when you will draw the graph, when you will plot the graph, your graph will be the rectangular hyperbola like this.
Yes, sir.
Because resistivity, your graph will be like this. Here you will have the resistivity, and here you will have the temperature.
Yes, sir. So can you scroll up? Okay, thanks. Just a minute. Just a second, scroll to the graph.
Yeah. So with increasing the temperature, the resistivity of the semiconductor will decrease.
Decrease, yes. Yes, sir. Done, sir.
So next question is using Ampere circular law. I have completed this part here. Ampere circular law, where we have done. This I have done now, this part.
Yes, sir. Yes.
So you can see from here also. And next part is drive the formula for force between two parallel
plate conductors. Yes, sir. We did that.
In the last class we have done.
Yes, sir. Then there is state two factor on which internal resistance depends.
No, there is one more question before that. Drive from find two for two cells with EMF E1 E2. This question I have given in the assignment. This question I have given in the assignment here in the current electricity.
Parallel plate. Yes, sir. I have done here.
I think I have given in the parallel combination.
Yes, sir. It will be V is equal to E plus I.
This question, same question. Yes, we have solved here also.
Yes,
we
sir.
got
Yes.
this answer.
Yeah.
So same question you have.
Yeah.
And the last question is
state two factors on which.
This is a theoretical question. The state two factors on which the what they are saying internal resistance. So you should know what is the cause of the internal resistance and how the cell is formed. Means in cell we have the electrolytes and the electrodes. We have the electrolytes and the electrodes. Okay, so there is some surface area of the electrode, and electrodes are placed far apart. So two factors on which the internal resistance depend will be the surface area of electrode. More the surface area of electrode, less will be the internal resistance. Okay, and more will be the distance between the electrode, more will be the internal resistance.
Yes, sir.
And anything else left? Last question.
Yes, sir.
They are saying
the battery of a cell car has 12 volts.
Okay, just. They are saying the storage battery of a car has an EMF of 12 volt. If the internal resistance of the battery is 0.4 ohm, what is the maximum current that can be drawn? Very, very easy question. Last question, na?
Yes, sir.
Question number?
10B.
10. So we have a cell This cell have some internal resistance, and they are saying find the maximum current, or what is the maximum current that can be drawn from the cell. So
Yes, sir.
basically they are saying calculate the maximum current. So this is the internal resistance, this is the
Yes,
EMF,
sir.
and suppose this is the external resistance R. So the condition for the maximum current, you should know. Condition for the maximum current in the circuit, this resistance, external resistance should be 0. External resistance 0. When your R is equal to 0, current will be maximum.
Maximum.
Now your R becomes 0. So you can find the current. Current is equal to E by R, simply E by small r. So this will be your maximum current. Put the value.
Yes, sir.
What is E?
E is 12.
12 volt. Internal resistance 0.4.
Yes, sir.
So this will become 30
Yes, sir.
ampere. Just write down this. So I think your paper was easy. Okay.
Yeah.
And most of the part I think we have covered in the class also.
Yes, sir. Yes, sir. Done, sir.
Okay, so now we will discuss the topic that torque on a current carrying coil in magnetic field.
So just a minute, sir. Just a minute.
No problem. Start.
Yes, sir. You can continue, sir.
Okay. So I have discussed. Now I can remove this. Okay.
Yes, sir. You can.
So this is torque.
On acting on a circular coil.
Circular coil. Not a circular coil. This is the coil we have, and
Yeah.
this is the magnetic field. And this magnetic field is making an angle theta with the plane
Yes,
of
sir.
the coil. Okay. And
Yes.
A is the area of the coil. Then your torque on the coil is given by mv cos theta. What
Yes,
is
sir.
m? M is the magnetic moment.
Magnetic field. Magnetic moment. Sorry. Yeah.
Yeah.
Magnetic field is B.
Yeah.
Cos theta is
Magnetic moment. And B is the magnetic field. Theta
Yes,
is
sir.
the angle between the magnetic field and the plane of the coil. Magnetic field and the plane of the coil.
Plane of the
So
coil.
yeah. Now suppose we have this coil. Same coil we have. This is the coil we have, and the current in this coil is in this direction. This is the value of current. Current in the coil is in this direction. Okay. And this is the axis about which the coil is rotating. and here is the magnetic field. This is the magnetic field here, and here is the magnetic moment.
Yes, sir.
This is the magnetic moment, and this magnetic moment is perpendicular to the plane of the coil. So this angle is given as theta. So this angle will become 90 minus theta. Okay, so I am saying this 90 minus theta as alpha. So what is alpha? Alpha is the angle between
Magnetic moment and
magnetic field. Very good.
Yes, sir.
Angle between magnetic moment vector and the magnetic field vector. So see, we have the formula of torque mv
Yes,
cos
sir.
theta.
Yes, sir.
Theta. Now from here, I can find the value of theta. This is alpha. This is theta. So alpha plus theta is equal to, you can take 90 degree. This angle, whole angle
Yes,
will
sir.
be equal to
Yes, sir.
90 degree.
90 degrees.
So this alpha plus theta is
It will
equal
be
to
cos 90, which is
yeah. So theta you can calculate from here, 90 minus alpha. Now put the value of theta here. Instead of theta, we will put 90 minus.
90 minus theta.
So remember, this cos 90 minus theta is equal to sine theta.
Yes, sir.
So we have cos 90 minus theta, 90 minus alpha means sine alpha we will have. So your formula will be mv sine alpha. This formula is more important than this formula.
Yes, sir.
So mv sine alpha you have. Alpha is the angle between the magnetic moment and the magnetic field. So I can write this formula in this form, m cross v. In the electrostatic, we have seen that the torque on the dipole is P cross E. What is P there? P was the dipole moment. And E is the electric field, and here M is the magnetic moment. Suppose I have just calculated this torque for one coil, for one turn of the coil. Suppose if there are n turns in the coil, if capital N turns in coil, then this formula will be modified to N M V sine alpha. NMV sine alpha. NMV sine alpha. Just note down this from here.
Yes, sir.
This is your same coil. Just write here. This is your same coil.
Yes, sir.
Here A B C D. Okay, A B C D. I am writing here. This coil is same as. Again, this coil is A B C D. Just write down this.
Sir, scroll down. Done, sir.
Okay. So now there are some special cases regarding
Yes,
the
sir.
torque on a coil. So this is the coil ABCD, and
Yes,
this is the
sir.
magnetic field in this direction. This is the
Yes, sir.
magnetic field in this direction. Now, when you will calculate the magnetic moment, direction of the magnetic moment. So direction of the magnetic moment will be perpendicular to the plane of the coil. Okay. So you can say the magnetic moment will be like this. Your magnetic moment will be like this. This will be the direction of the magnetic moment. And this magnetic moment will be perpendicular to the magnetic field,
Yes, sir.
because magnetic field is in this direction, x direction, and your magnetic moment is towards z axis.
Yes, sir.
So theta is the angle, 90-degree angle is between the magnetic field and the magnetic moment. So torque on the coil is given by mv sine of alpha. Alpha is the angle between the magnetic field and the
Yes,
magnetic
sir.
moment.
Magnetic moment.
Here alpha is equal to 90 degree.
Yes, sir.
So put the value of alpha. This will become mv sine 90. So your torque value will be mv, and this torque will be the maximum torque.
Yes, sir.
This torque is maximum
Maximum torque.
because this sine 90 is maximum, because this value is maximum.
Okay, sir.
Okay, just wait. I will give you a time. Okay, for
Okay.
noting down. Okay, so here is another case. This is the last case. Here, see, this is your coil. This is your coil. Suppose this is your coil ABCD. Okay, here magnetic moment is in the same direction of the magnetic field. So alpha is equal to 0 degree.
Yes, sir.
So torque formula will be tau is equal to mv sine 0, and that
Yes,
this
sir.
torque will become 0. For this case, alpha is equal to 180 degree. Why? Because magnetic moment and the magnetic field are in the opposite direction. So alpha is equal to 180 degree. So tau is given by mv sine 180 degree. So sine 180 degree is equal to 0.
Yes, sir.
Sine 180 degree is also equal to 0, and
0.
sine 0 is equal to 0. So when the magnetic moment is in the direction of the magnetic field, then also the torque is equal to 0. When the magnetic moment is in the opposite direction of the magnetic field, then also the torque is equal to 0. When the magnetic moment is perpendicular to the magnetic field, then the torque will be maximum. Okay, now you can note down.
Yes, sir.
So write the heading special cases,
Yes, sir.
and then you should write this.
Second, scroll down second case. Done, sir.
So we have one question on it. This question is from NCRT. Very good question.
Yes.
So in this question, they are saying a 100-turn closely wound circular coil of radius 10 centimeter carries a current of this. Means a circular coil having a current of 3.2 ampere,
2 ampere.
And having a number of turns 100. What is the field at the center of the coil? Very easy. Second, what is the magnetic moment of the coil?
Yeah, so mu 0 Ni by 2.
Yeah, you will just apply the formula and you will get the answer.
Yes, sir.
Okay, see, this is the coil. So a circular coil is there. A circular coil is there, and what is given in this circular coil? Number of turns are 100. There are 100 turns.
Yes, sir.
Capital N is given as 100. Capital N is representing the number of turns, and radius is 10 centimeter. When you will convert this in meter, it will become 0.1 meter. And current in the coil is given as 3.2 ampere. So they are asking, what is the field at the center of the coil? So field at the center of the coil is given by mu naught Ni divided by 2R. Mu naught is 4 pi.
Yes, sir.
10 to the power minus 7. Number of turn 100. And current is 3.2 ampere. This is divided by 2 into radius 0.1. We'll get the answer 2 into 10 to the power 3. Tesla. Okay. if you want to calculate the direction, but here the direction of the current is not given. So for the direction of the magnetic field at the center, you will apply the right hand rule. Just
Yes, sir.
curl your finger along the sense of current. Your thumb will give you the direction of the
Outwards,
magnetic field
outwards.
outwards. If the current is in this direction, if the
Yes,
current in
sir.
the opposite direction, then the magnetic field will be inwards. Okay, and second part, I mean this is the A part now. This is A part. Now B part. In B part, they are asking the magnetic moment. So magnetic moment of the circular coil is given by Ni into A. Area of the circle or circular coil will be pi r square.
Yes, sir.
So this is pi r square means 0.1 square. So magnetic moment, number of turns 100, current is 3.2 ampere, and area is given by pi into 0.1 square. So approximately you will get the answer 10 ampere meter square. B part. Now C part is different. C part is different. See here, for the C part, the coil is placed in a vertical plane. The coil is placed in a vertical plane and is free to rotate about a horizontal axis which coincides with its diameter. Okay, which coincide with its diameter. A
Yes, sir.
uniform magnetic field of 2 Tesla is in the horizontal direction. Is in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. Initially, the axis of the coil is in the direction of the field. So see how we will draw the diagram. So we will have a coil like this. In a vertical plane, we will have a coil, and suppose this is the axis of the coil in the horizontal plane
Yes,
and
sir.
horizontal axis, and this coil is rotating towards this axis like this coil is like this, and this coil is rotating like this. Okay,
Yes,
and
sir.
this is the axis about which the coil is rotated, and uh, here also given this axis is also coincides with its diameter. Okay,
Yes, sir.
this is also coinciding with the diameter of the coil. So magnetic field is in the horizontal direction, means magnetic field will be like this. Magnetic field will be like this. This is the magnetic field. Okay, so can you tell me what will be the direction of the magnetic movement? Magnetic movement will also be horizontal because this
Yes, sir.
coil is in the vertical plane. So when you
Yes,
will
sir.
apply the right hand rule for the magnetic movement, when you will and just for the right hand rule you will apply, then you will get the direction in this direction of the magnetic movement. But the direction of the current is not given here.
Yes,
Direction of
sir.
the current is not given, but
Not
we know
given.
that. But we know that the magnetic moment will always perpendicular to the plane of the coil. Okay, so we can take the magnetic moment like this. Okay, this is the plane of the coil, so magnetic moment will be perpendicular to the plane of the coil. So angle alpha will be 0 degree. Okay, so what will be the torque?
I mean, yeah, it will be.
Zero. You are right,
Yeah, it will be zero, right?
because this is sine 0 na, and sine 0 is
Sine
0.
zero is zero.
Torque initially is the situation of the coil is this. Now initially, finally what they are saying, the coil rotates through an angle of 90 degree under the influence of the magnetic field. What are the magnitude of the torque on the coil in the initial condition we have calculated, and the final position. For the final position also we will calculate the torque when this coil is rotated 90 degree angle. When this coil is rotated 90 degree angle. So when this coil will be rotated 90 degree angle, see what will happen. We have to make another diagram for this. When you will rotate this coil 90 degrees, so this coil will become like this. You have just this is your coil, okay, and you have just rotate this coil like this, so it will become like this. A magnetic
Yes,
field
sir.
is already given. Magnetic field is already given along this axis. Magnetic field is along the horizontal axis. Now magnetic moment, we know, always perpendicular to the plane of the coil. So magnetic moment in this case will be like this. This will be the magnetic moment. This will be the magnetic moment. So angle between the magnetic field and the magnetic moment is 90 degree. See, this is your plane of the coil, and
Yes,
your
sir.
magnetic moment will be perpendicular to the plane of the coil. Magnetic
Yes.
moment will be perpendicular to the plane of the
Plane
coil.
of the coil.
If your coil is like this, then your magnetic moment again like this, perpendicular to the plane of the coil. If your coil is like this, then your magnetic moment like this. Okay, always perpendicular to the
Plane of the coil.
yeah. Finally, we have this, and here alpha is equal to 90 degree. So apply the formula of torque, mv sine alpha, mv sine 90. So in this case, sine 90 is there. So torque will be maximum.
Yes, sir.
Torque will be maximum,
Maximum.
m into v. The both the values we have. The value of m we have.
Yeah, 2 to 1.
M is 10 here, na?
Yes,
10.
sir.
So put the value of m 10. And magnetic field is 2 Tesla given in the
Yes,
question.
Sir. 20.
2 Tesla. This is given in the question. So this will become 20. Unit of torque is Newton meter.
Yes, sir.
Because torque is equal to force into distance, force into perpendicular distance from the axis of rotation. So unit
Yes,
of
sir.
force is Newton. Newton of distance, oh sorry, unit of distance is meter. So Newton meter we have. Last part is related to the rotational motion of 11th class. They are asking in the D part, what is the angular speed acquired by the coil? What is the angular speed acquired by the coil when the coil is rotated by 90 degree? Moment of inertia given 0.1 kg per meter square.
What's the formula for this, sir?
Yeah, this is the coil. Now you have rotated this coil 90 degrees. So what will be the angular speed of the coil? Angular speed. So see this case. Now here the coil is rotating. In this case, the coil is rotating. So you can say that in linear motion, you have this formula: force is equal to mass into acceleration. Linear motion. But in rotational motion, you have torque is equal to moment of inertia into alpha. This tau is torque.
Yes, sir.
I is the moment of inertia. Moment of inertia. Alpha. This alpha is something different. This alpha here is the angular acceleration.
Okay, yeah.
So torque is equal to I alpha. So what will happen? This coil will rotate like this. Okay, there will be the torque on this coil due to the magnetic field, and that torque we have calculated already. 20 is the torque.
Yes,
Torque
sir.
will be 20 Newton meter.
20 Newton meters.
And I is given as 0.1
Yes, sir.
kg meter square. Okay, and the coil is rotated through an angle of 90 degree. So here from this with the help of this formula, we can find this alpha first. So torque is equal to I alpha. This is 0.1 into alpha. So alpha is equal to 20 divided by 0.1. So this will become 200 radian per second square.
Second square.
Yeah, unit of this alpha means angular acceleration is radian
Yes,
per
radian,
second
yes,
square.
sir.
Okay. So now you have rotated the coil through theta. and
Yes,
that
sir.
theta is equal to 90 degree. Now we can convert this theta into radian by multiplying is by pi by 180 degree. So this will become pi by 2 radian.
2 radian. Yes, sir.
They are asking the angular speed. They are asking the angular speed.
Speed.
Angular speed acquired by the coil when it is rotated by 90 degree. So your coil is initially like this. Finally, your
Yes, sir.
coil is rotated like this. So
Yes,
initial
sir.
velocity, initial angular velocity of your coil, because initially this coil is at rest. Okay.
Yes, sir.
Now finally this coil starts the rotational motion. It starts the motion.
Yes, sir.
What will happen here in the initial condition? The angular velocity of the coil will be zero. But when this coil start the rotation in this position, when the coil will shift an angle of 90 degree, then we have to calculate the angular velocity. There will be some angular velocity. Then we have this v square is equal to u square plus 2as. This equation we apply in linear motion. Here this v represent the final velocity, u represent the initial velocity, a is the acceleration, s is the linear displacement. But in case of the rotational motion, we apply this. Omega final square is equal to omega initial square
Initial square.
plus 2 into alpha into theta. See here. Here is final linear velocity square. Here is final angular velocity square. Here is final initial velocity square. Here is initial angular velocity square. Here is 2. Here is 2. Here is linear acceleration. Here is angular acceleration. Here is linear displacement. Here is angular displacement. So this final velocity, final angular speed of the coil we want to calculate. Initial angular velocity is 0. 2, alpha is 200, just calculated the alpha is 200 radian per second square, and theta is pi by 2. From here you will get the final angular velocity 20 divided by pi by 2. The unit of angular velocity is radian per second. So this is your final answer.
Yes, sir.
This is final angular speed. So this part maybe you will not get properly, because here the concepts of 11 class are there, and but one by one I have told you all these things.
Yes,
And
sir.
one thing more, I'm just giving it 2 star because this is related to some concept that you have used in the 11th class. Okay, this okay, and this is also okay. Okay, just
Yes,
note
sir.
down. So what you should do now, you do you have the NCRT?
Yes, sir. I have it.
What you
It's
should do?
marked, sir.
Yeah, NCRT. So here this is example 4.11. Write
Yes,
on
sir.
your copy example 4.11. This is
Sir,
from
I
the
wrote it,
chapter
sir.
4. Yeah,
I wrote it.
and this question you will get in NCRT. Okay, write down
Yes,
the
sir.
question
Chapter
from here.
4.
Yeah,
Yes.
chapter 4. So and you can just write down the answer only.
Yes, sir.
Yeah, I am just coming.
Second, scroll down.
Scroll down.
Yes, sir. Second, scroll down.
Yeah.
Done, sir.
Done. Okay. So write down some questions for the homework that these questions are important questions. Like
Okay, okay.
should try example number 4.11. I have told you this is the example 4.11 we have already
Yeah.
done. Okay.
Yes, sir.
Now just try from the exercise of NCERT. Exercise you will do question number 4.24. Okay, and this question is very important question. Just try
Yes,
it
sir.
by
Yes, sir.
yourself and write down this, and this is your homework.
Okay, sir.
Based on the same concept.
Yes, sir. Done, sir.
Okay. So last topic of this chapter, moving coil galvanometer. Moving coil
MCG.
MCG. So moving coil galvanometer. So moving coil galvanometer is based on the same principle
Yes, sir.
that we have studied. Whenever a
Yeah.
current carrying coil is placed in the magnetic field,
Permanent between two permanent magnets, torque is produced.
yeah, torque will be produced in that coil. So what is the
Yes.
galvanometer? It is a device used to detect the
Detect
current
feeble
and
current.
voltage.
Yeah. Yes, sir.
And principle is this: a current carrying coil in magnetic field experiences a torque.
Torque.
So see the construction. So this is your here in what happens in the moving coil galvanometer. On a cylindrical iron core, a coil is wounded, a wire is wounded, and that is known as the coil. Okay, this is the coil. Okay,
Yes, sir.
this yellow color thing is a coil. This orange
Yes,
color or
sir.
yellow color thing you can say is a coil. And these are the magnet. Okay,
Yes, sir.
these are the magnet. This is the pointer, and this is the scale, and this is the pointer. Scale and pointer. So what is happening? This coil is bounded over the iron core, cylindrical iron core, and this coil you can say is in the magnetic field produced by the north pole and the south pole.
Yes, sir.
So this coil will rotate like this.
Yes, sir.
Due to the torque, this coil will rotate like this.
Yes, sir.
So now we will see the top view. We will see the top view of this. So top view is this. In exam, you will draw the galvanometer like this. This is the top
Yes,
view.
sir.
So in top view, this is the cylindrical core, and on that cylindrical core, this wire is wounded. Means this is the coil. Okay, this is the
Yeah.
coil having n number of turns. This is the north pole. This is the south
Yes,
pole,
sir.
and from here, a pointer is attached. This is the pointer, and this is the scale of the galvanometer.
Yes, sir.
These are the markings on the galvanometer scale, and theta is the deflection
Angle.
Yeah, theta is the deflection. Means suppose initially your pointer is here. When the current is in the galvanometer, the pointer will deflect. So this is the deflection.
Yeah.
This is the top view, and this your pointer is attached with somehow
Spring.
with a spring. So the cylindrical iron core. So this is a construction.
Yes, sir.
So now there are some terms that I will use. Area of the cross section of each turn. A is the area of the cross section of the each turn of the coil. So this is the coil. Okay, no need of this. Here we will have a coil. Just for the understanding, it is required. This coil is having the end turn, and this coil is having the area A. Area of cross section of each turn of the coil. B is the magnetic field produced by these magnets.
Yes, sir.
I is the current through the
Current
galvanometer.
passing through the galvanometer.
Through the galvanometer. Okay. Or you can say current through the coil also.
Yes,
Theta
sir.
is the deflection in the galvanometer. This theta
Yes,
is
sir.
the deflection in the galvanometer. When the current will pass, there will be the deflection in the galvanometer.
Yeah.
Magnetic movement of the coil. This coil
M and I.
M is equal to NIA. These things I have already discussed. Okay.
Yes, sir.
M is equal to NIA. Now, what will happen basically? What will happen? The moral of the story is that when the coil is placed in the magnetic field, the coil is having a current. So what will happen in a magnetic field? There will be some torque on the coil. There will be some torque. The coil will start rotation.
Rotating due to torque.
Start rotating. Yeah. This is the coil, and suppose this is the coil in the galvanometer. And when the torque will be there on this coil will try to rotate like this. To rotate like this, and a spring will be attached. This coil will try to rotate, but the spring will not rotate. Yeah, a spring will oppose the rotation motion of this coil. Okay.
Yes, sir.
A spring will oppose the rotational motion of this coil. Okay, so there will be some restoring torque in the spring that will oppose the motion of the coil due to the torque, due to magnetic field. So simply we can say torque on the coil. We will use the formula of the torque on the coil. Just a minute. So you can write here torque on coil due to magnetic field, due to magnetic field. What is the formula of the torque? Torque is equal to mv sine alpha.
Yes, sir. Sin alpha.
Alpha is the angle between
Angle between the magnetic
movement.
moment and the magnetic field.
Okay. There is one more thing here. There is one more thing here. This thing.
Yes, sir.
These are the magnetic field lines. These
Yes,
are
sir.
the magnetic
Magnetic
field lines,
field
and
lines.
these lines represent the radial magnetic field.
Yes, sir.
Now, what is radial magnetic field? Okay. So radial magnetic field is basically the magnetic field like this. This is your coil, and this will be the magnetic moment.
Yes, sir.
Coil. This is your coil, and this is your magnetic moment. When the coil will rotate, the direction of the magnetic moment will also change.
Yes, sir.
But what we want that the magnetic field and the magnetic movement should be in the same direction.
Same direction.
So what we will do, for that there is a requirement of the radial magnetic field. So what will happen? Suppose this coil is rotating like this.
Yes, sir.
Like this. So now the direction of the magnetic movement is in this direction. But due to the radial magnetic field, the radial magnetic field will now again is in this direction. So you can say the direction of the magnetic movement and the magnetic field will be same. Suppose now coil is rotated like this.
Yes, sir.
Now the magnetic movement is in this direction. Due to the radial magnetic field, the direction of the magnetic field will also be in this direction.
Yes, sir.
So this is the work of the radial magnetic field to make the angle zero.
Between magnetic
not zero,
and
90 degree. Okay.
Yeah.
To make the angle 90 degree between the magnetic field and the magnetic movement.
Yes, sir.
Actually, one thing we have missed here. See here, this is your coil.
Yes, sir.
Okay. This is your coil, and this is your coil, and this is the direction of the magnetic movement.
Yes, sir.
So when this coil will rotate, the direction of the magnetic moment will change.
Yeah.
Okay. But what we want, there should be the angle of 90 degree between the magnetic field and the magnetic moment.
Yes,
so
sir.
when this coil will rotate like this, so magnetic field will be like that, radial magnetic field will be like that, no matter in which direction this magnetic movement will be. The magnetic field will always be perpendicular to the magnetic moment. Means alpha, the value of alpha will equal to 90 degree
90
always.
degrees. Yes.
Yeah. So you will write here alpha is equal to 90 degree.
Yes, sir.
You can say here the magnetic field will always be perpendicular to the magnetic moment. Always for the radial magnetic field.
Yes.
So
Sir.
what is the value of alpha? 90. Now here
Yes.
alpha is equal to 90. We will put. What is the value of sine 90?
1.
Yeah, 1. So you will get this torque is equal to mv. So put the value of m. M is equal to NIA.
NIAB.
NIAB. A, and this will become NIAB. So this is your torque.
Yes, sir.
Due to the magnetic field. on coil. Now what will happen? This due to this torque, the coil will rotate, but the
Rotate.
spring will
Resist the motion.
resist the motion, and there will be some torque, restoring torque will be there. Okay.
Yes.
So suppose K is the restoring torque per unit twist of a spring. Per unit twist means the coil will rotate, the spring will be twisted like this.
Yes, sir.
Spring will be twisted when the coil will rotate like this. See here, this is the coil. Here one spring is attached, so this coil
Yes,
will
sir.
rotate. Here spring will be
The
twisted.
spring will twist. Yes, sir.
Yeah, the spring will twist. So there will be some restoring torque. Okay, so you can say restoring torque in a spring, that is represented by tau suffix
Tau
r,
R.
and this is given by k into theta. Means suppose the coil is rotated at an angle of theta,
Yeah.
then the spring will also be twisted through an angle theta.
Yes, sir.
Okay, for one twist, for unit twist, restoring torque is k. For theta twist, restoring torque is k theta. Simply unitary method.
Yes, sir.
Okay. Now what will happen? This coil is rotating like this. The spring
Yes.
is trying to rotate this coil in the opposite direction. There will be a time when the restoring torque and the torque due to the magnetic field will be same. So you can say in equilibrium, T is equal to TR. T is given by NIAB. Okay.
NIAB is equal to K theta.
Yeah, NIAB is equal to K theta. NIAB is equal to K theta. From here you can just find the value of current K theta divided by NAB.
NAB.
So this K is constant because this is a torsional constant. This is also known as torsional constant. This K is also known as torsional constant.
Yes, sir.
So this K is constant, number of turns will remain constant, area and magnetic field. So you can say the current is depending upon theta. Current is
Yes,
directly
sir.
proportional to theta. More the current, more will be the deflection.
Well,
Theta,
theta,
what
yeah.
is theta? Theta is the deflection.
Deflection.
In galvanometer, and what is I? Current in the
Current.
galvanometer.
Yes.
Okay, note down. In exam, you will draw the moving coil galvanometer like this.
Yeah.
Yeah.
So can you scroll down? Yeah, I did that, sir.
This part, na?
Yeah, this part. So I can scroll down.
Okay.
Sir, a little bit more, sir. Till K.
Okay.
Yeah. Done, sir.
Okay, just two topics are there: current sensitivity and voltage sensitivity. Then I will wind up. Okay.
So now we have to do that.
Okay, so we will do in the next class. Okay, no
Sir,
problem.
because I have to go out. So
Yeah, yeah,
that's it.
okay, I know. Okay, so no problem. So in the next class, okay, just you can prepare.
Yeah, MCG.
No, no, no. You should not prepare this moving coil galvanometer. And before this topic,